Hello, everyone. Welcome to what's the name of my class? How to lie and cheat, or lying and cheating, how to catch the bad guys or become them using math. This is going to be a really fun class. We're going to talk a lot about statistics and generally just sort of
lying.
lying.
Okay, so
I'm going to go around and give everybody 2 post-it notes. I know some of you already have them, but if you don't, let me know.
So we do want to start off with a disclaimer. We're going to tell you about real frauds that actually happened, but we're not going to be using the real numbers from the actual frauds. And
Everybody has post-it notes.
We may take true stories and tell them in a way that's kind of simplified in order to make it fit into the class. So our disclaimer is that not everything we'll tell you is necessarily true, but it's not maliciously false either.
So everything that we're talking about has happened. We've got like academic studies that have like looked at it and shown it. We can show you guys those studies later after class if you're interested.
More importantly,
but the numbers that we use are going to be a little bit altered so that they can make sense. Come on in.
More importantly, on our blog later today, we're going to post some sources if you guys do want to. .net. We're going to post some sources if you guys want to learn more about kind of the backstories behind and the real sort of the more detailed versions of the things we're going to tell you today. Then later today, or maybe early tomorrow, we're going to post on our blog, mathandmaking.net. Okay, so come on in. There's chairs sort of scattered around. There's.
Okay, here. I will set this up if you want to get it.
Yeah.
Okay, so what we're going to talk about first is how to sell drugs, which is kind of fun. So let's say that we are a big pharmaceutical company, and we have spent a lot of money, $1 billion, to get a new drug to market. In this case, we'll call it Risperdal. Maybe we have a vested interest at this point to make sure that we can sell our drug to people. Now this is like, we're talking pharmaceuticals and stuff like that, something that a doctor would give you. But we really want to be able to sell this in the United States because we've spent a lot of money. Now, in order to sell drugs in the United States, you have to first pass sort of a FDA approval.
Yeah.
Let's see what it is.
We're kind of jumping the gun a little. Because even before you want to do that, you want to
what we want to do right now is we want to
not talk about that yet.
We want to convince you that our drug is safe to use. That's what we want to talk about.
It's not that that's bad.
Okay, we're gonna start with a smaller scale to help this make sense, and then we're gonna talk about.
Sorry, Jay.
That's okay.
I should figure out how to be more supportive.
No, okay. So we're gonna talk about sort of this smaller scale experiment.
So let's talk about a different thing for a second. Suppose Jake and I are drug dealers, but we're not drug dealers of the cocaine sort of drug. We're drug dealers of the $1 billion fix some serious illness type of drug. And we've made 2 drugs, and we want to sell you one of them. We want to convince you that drug 1 is better than drug 2 because it's more expensive. And so we conduct a study, and so I'm going to now try to convince you that drug 1 is in fact better for drug 2 than drug 2 for you. And so I conducted a study on. There were two groups that were involved in the study, and some people were cured, some people were not cured. And so how many men were cured? Well, 10 men were cured, 1 man wasn't cured for drug 1, 10, 100 for woman, 100, 100, 1, and 100.
Now you might look at those and think, these seem like a little bit of weird numbers. Here, go ahead and sit down. And here's, there's 2 post-it notes here, my friend. All right, so you might look at this and say, these seem like weird numbers. And it turns out that if we're gonna when we look at this, we can perform the analysis and find something a little bit weird that comes out of this.
So I want to convince you that drug 1 is better than drug 2, right? That's my goal, because drug 1 is more expensive, so how am I going to do that? Well, look at it. Let's just look at drug 1 and drug 2 for men. Okay, well, drug 1 is clearly better for men because it has 10-to-1 ratio instead of 1-to-1 ratio for cured to not cured. So for men,
drug 1 is better. And actually, the same thing is true for women, right? In this group, it cured 10 women out of 100, or 10%, kind of, well, not really, 10 women, and it didn't cure 100, and in this one it only cured 1 woman out of 100. So clearly drug 1 is also better for women.
So,
right?
Are you guys ready to buy drug 1 from us?
Seems like that's kind of a good thing. If you're a man, it's better. If you're a woman, it's better. Seems to work out.
There's
Seems
only
like that's
one
gonna work.
problem with the analysis we've given to you, so we've kind of lied. Because look at drug 1 versus drug 2 for people. How many people were tested on drug 1? Well, that's 10, 11, 21, 121. And for drug 1, how many out of those 121 people did it cure? It cured 20. On the other hand, for drug 2, how many people were tested?
Let's see. Is there some? Go ahead and keep doing this. I'm going to try and find some spaces.
There was 100, 200, 201, 301 people tested, and out of those, 101 were cured. So drug 2 is clearly significantly better than drug 1 for people. So actually, this is great for Jake and me because we want to be able to choose whether to sell you drug 1 or drug 2. So depending on which analysis we give you, we can convince you to buy one or the other depending on our mood, which is really great.
Which is kind of powerful and also a little bit sketchy.
So how did we manage to make this work? Well, the key thing to notice is that these sample sets for each of these 4 quadrants are not the same size. In particular, even though we only cured 20 out of 121 people with drug 1, we took a small group containing a lot of the cured people and gave that group equal value to all the other groups that we were testing. So even though there aren't that many people being cured here, they get a whole lot of value because they're 10 out of 11 of the people that we've put in this group. And so this idea of grouping is actually really powerful. Suppose you have some data and you want to make one drug, for example, look better than the other drug. Then maybe you can find some sort of grouping, maybe men or women, maybe blonde-haired, brown-haired. You go and you look for some sort of grouping that will allow for you to manipulate it to make one thing look better than the other.
And this sounds kind of interesting, right? Like, okay, cool. So we can decide based off of using some math whether or not to make drug 1 look better or drug 2 look better. And at this point, you might be asking yourself, well, okay, that's kind of interesting, but does this actually apply? Has anybody ever actually done something similar? And more importantly, how could we make money off of this in real life?
Right.
Well, it turns out, and this is what I started to talk about in the beginning of class, it turns out that this is something that some people actually did. A very large drug corporation that was trying to manufacture some drugs for some people to help them feel better. They needed to convince everyone that their drug was safe, and they did something very similar to this with this whole grouping problem.
So this is actually a really recent scandal, and it's actually a pretty big deal. Johnson & Johnson ended up pulling off this scandal where by somehow lying through statistics, they managed to get a drug past the regulation agencies that it shouldn't have gotten past. And by doing, and by managing to do that, they ended up eventually getting fined once they got caught. But they only had to pay something like $1 billion after making $10 billion in profits from getting this drug through the regulations. So how did they do it? So they...
Okay, so basically to pass, go ahead and write down the stuff. So to pass the FDA approval, basically what Johnson & Johnson needed to do was they needed to show that they had basically a negative side effect rate of 5%, or I'm sorry, 0.5% or 5%?
We're going to go with 0.5%.
0.5%. So like really low rate of like bad things happening with this drug, right? And so what they did is they went out, they conducted a study, they gave, this was part of like this drug experimentation, which is pretty normal, but they went out and gave these drugs to a whole bunch of people, and then they looked and saw if it helped their illness or if it made them feel sick, that sort of a thing. And when they did this, they actually came back and found something that they didn't really like. And when they looked at it, they saw that 30 people out of 1,000 people that they tested had a negative side effect. which is 3%, which is about 6 times more than they could actually accept.
So this was a big deal. These guys had just spent $1 billion developing a drug. They needed to have less than 0.5% negative side effects on people, and they were getting 30 of 1,000, which is more than 6 times as much as they could possibly afford. But they weren't ready to give up yet, because remember, these are the greatest liars and scammers around. So they started to brainstorm, and so in order to sort of see how they started to brainstorm, we're going to do a quick activity. So I want everyone to randomly pick a number 1 to 3, okay, and write that down on one of the post-it notes in front of you. Try not to base your, try to sort of, you know, it doesn't have to be completely random, but you know, just come up with some random number.
Okay, everybody have their number? Okay, so could we want to do this by having people stand? We've got a kind of a tight room. Okay, so
Can you raise your hand if you have a 1?
You have a 1? Okay, so can you raise them up high, please, so we can see it really easily? Okay, cool.
Okay, can you raise your hand if you have a 2?
You have a 2.
Okay.
Lots of 2s.
And can you raise your hand if you have a 3? We have 1 3.
We have 1 3. Cool.
Okay.
Way to go.
So this is not quite how we anticipated it turning out.
No, it'll be fun.
Okay. So raise your hand again if you have a 1. Just real quick. Okay. So because it turns out that in this study that we're running right now, the 1s correspond with people who are having side effects with our drugs. So we need you to raise your hand again. Stand up if you have a 1. We need to find out. We need to just figure out how to get rid of you from our study somehow.
Okay.
You know.
This is tricky.
Okay, so let's see. What can we do to get rid of the 1s? There's. Okay.
I'm not sure. Maybe not the 1s. What if we have our 3s stand up really quickly?
No, that's not fair. It's only 1 3. Jake, we're up
I
to the
think
challenge.
No, let's do the 3. Let's keep the class moving. You can go ahead and sit down. Thank you. Okay, so let's say in this case we want to be able to get rid of. We need to be able to get rid of a group in our study. And so what we're going to do is we're going to say, well, you know, if you're wearing a shirt that's striped and has yellow on the top, then
You're probably not eligible for the study.
then something about people who wear shirts that have yellow on the top and are striped, it doesn't work for the
I've
study.
met people like that. They're the kind of people who lie in studies. I just don't think we should include, you know, I forgot to mention this before we conducted the study, Jake, but I really don't think we should include those people.
Okay.
Yeah. So actually, you can sit down. You didn't get to pick 3 after all. So actually, the study was great. There were no people, not a single person ended up.
Nobody ended up picking 3, except for, you know, this one group,
Who
the
doesn't
people
count.
who wear yellow shirts, but they don't count
And
because
this
they
is
wear,
actually
you know, the yellow shirt.
exactly what Johnson & Johnson did. Was they said, okay, well, we need to find some group that we can ignore that contains a lot of the people who got sick. And then by ignoring them, maybe we can get our numbers to look better. And so they thought, okay, what's one thing we could group according to? We could look at age. So looking at age, I think their study was kind of equally distributed among the people of each age. So if you look at the number of participants,
I'll write this one down.
if you look at the number of participants of each age range,
We don't need to be all the way over here. Let's move more to the center. So it's a little bit easier.
if you look at the number of participants of each age range, it turned out that there were sort of 3 age ranges they looked at, and the number of participants of each age range were sort of evenly distributed. So if they looked at 1,000 people, there was sort of something like 333-ish people of each age range that they looked at.
Okay. And these are all supposed to be the same.
Okay. And but what they noticed was something that was kind of interesting, which was that even though they looked at the same number of people in each age range, a lot of the people who got sick were actually in one age range in particular, the 9 to 12 age range.
So over here, so this is the number of people that we performed our experiment on. And over here, we're gonna see the number of people that got sick in our different groups here. So this is
One.
okay.
So we had 30 people who got sick in total, But the interesting thing to look at is, the people in the 13 to 16 age range got sick at a much higher frequency than everyone else. And so the Johnson & Johnson executives sort of thought about this for a minute. They're like, that's interesting. You know, Jake,
What is it, Bill?
I forgot to mention to you this before the study, but it strikes me that kids aged 13 to 16, they have a lot of hormones, don't you think?
Yeah.
Yeah, and
they do.
With that many hormones, they may just be getting sick all on their own.
Yeah, they might just be getting sick. It might have nothing to do with our drug.
I think it would be much more fair if we just sort of crossed those guys.
If we just
Why don't you just go ahead and cross those out, Jake?
didn't count our friends with yellow shirts.
Yeah,
Good.
I think that's probably for the better. And,
All right.
and then we should come over here and fix our number over here. I think this number actually should be, well, we don't have to count those 27, that's 3, which is less than 0.5%. Awesome.
Well, hey, would you look at that, Bill?
That
We can
is-
sell our
that
drug.
is- That is really awesome. Wow, Jake.
Yeah,
We're gonna make billions.
awesome.
Okay.
So this is a little bit wonky, and I think that you see something, but we're gonna talk about that in just one moment. So this is a little bit wonky. Quite clearly, if we're looking at this, on one hand, that feels a little bit wrong, right? That doesn't seem like we should be able to just take, we should just exclude a group because they got sick, and now our data looks better. And actually, this is a thing that you have to be very careful about when you conduct a study. You have to decide before you do the study how you're going to do this distribution, because otherwise, if you look at it and you see this, you're going to be tempted to be like, well, 13 to 16-year-olds, maybe they just get sick a lot, so we're going to ignore them.
You're not allowed to do, you have to decide how you're going to do your analysis before the study. Otherwise, you have the opportunity to be fraudulent. And since this class is about being fraudulent, we recommend you do your analysis after the study every time.
Because you can check this. Now, this is actually exactly what the Johnson & Johnson folks did. And in fact, they even did something else. We've lied to you twice with this. On one hand, they've done this, which is kind of just bad business practice. But they've also just made a really silly math error. And do you want to talk about that?
They didn't take away the 13 to 16-year-olds and the participants. They only took it away.
Exactly.
That's right.
Well done.
So in the actual Johnson & Johnson study, they did this. They said, it's 3 out of 1,000. We're great. That's wonderful. But if you're not going to count the sick people from age 13 to 16, you can't count the healthy ones also. You got to take out the whole. This is not 3 out of 1,000. This is 3 out of
666.
Which is not less than 0.5%.
So even though they actually took all these people out and did all of this thing, they made a really stupid math error where they just didn't take care of the denominator.
It's brilliant.
So on one hand, this is kind of a silly math error, right? This is something that should never have happened. But it did happen because these people, these Johnson & Johnson folks, really wanted to sell their drug.
Okay, so moving on.
And so with that, you can see, one way that they lied here is by messing with the denominator.
Okay. Next up.
Next up. What is next up, my friend?
Clumping with sticky notes.
Okay, let's illustrate clumping. Okay, so how many of you here have seen the movie Frozen? Can we get a raise of hands? Okay, so almost everybody. All right, cool. So now if you haven't seen Frozen, I'm sure you've heard of it at the very least. I want you, if you haven't seen Frozen, to just pretend for a moment that you have. And what we're going to do is on our second sticky note here that you all have, we want you to write a number for how much you liked Frozen.
So,
and this is going to be from 0 to 100. And what we want you to do is write a number on the sticky note that corresponds, like 0 is, Frozen, I've just heard too much about this, I really don't like it, this is just way overplayed. 100 is like, oh my god guys, Frozen, this is super awesome. That's sort of the distribution that we're looking at here. So, I want you guys to write down a number based off of how much you like Frozen, and has everybody written down their number? Okay, now what we would like...
Well, let's pause and give everyone a second in case they haven't written down their number yet.
Okay.
If you don't have a pencil, just raise your hand. We can pass one around. Okay.
Here, have
a marker.
Have a marker.
Okay. Could someone, if you have someone raising your hand near you, can you let them borrow your pencil?
Okay. And so now what we would like to do is, we originally wanted you all to like stand up and come to the board and do this, but we were kind of packed on space here. So what we're gonna do is we're gonna just walk around and collect your Post-it notes, and then we're gonna come over here and we're gonna stick them up on the board, corresponding to where those numbers are.
Yeah, so if you could just
Okay.
pass them on to the front. Thank you. Thank you. Thank you. Thank you.
Thank you very much. Can I get that back? Thank you.
Thank you.
Okay. 25. And you can keep the first Post-it note. That one's yours.
7,
Alright. And I guess you're
Awesome, great guys. So, what do we got? I've got 60, I got an 80, I got a 67, 66. The person who wrote, was this, I guess this is 69. 69, a lot of upper 60s here. We got a 10, we got a 5, we have a 0.
Well, some people really are not fans of Frozen here.
That's all right. We understand. We are fans of Frozen, but we still understand.
Okay.
We've got a 30.
So if we look at this, we can see it seems like people are kind of clumping together a little bit here. And it turns out when you run, if we have enough people here, this is called a feeling thermometer. This is sort of what this is called. And it turns out if we have enough people, and you ask enough people their ideas about something, take a feeling thermometer. It turns out what you end up with is a lot of clumping.
And so, in particular, let's look at the kind of numbers you get. Right? You have 5, 10, 25, 30,
Lots
50,
of-
55, 60s, 80.
Lots of divisible by 5 numbers. And that's because humans kind of like those numbers, right?
And you're going to go for natural fractions, like 3 25s, but no 26s and no 24s. There's a 50, but there's not going to be a 51 or a 49 unless someone's feeling smart aleck. And, there's an 80, and there's a few of you thought really carefully and put yourselves in the upper 60s, but that's just because you guys are special.
So what we've got here is a good illustration of sort of human behavior, and we like round numbers, and even if it's not exactly 0, 25, 50, 75, or 100, typically a lot of these numbers are divisible by 5, or kind of have this nice natural clumping, if you will, when you look at this.
So now suppose that you are trying to fabricate a study, and your name happens to be Liqueur. You happen to have a name, and the study you're trying to fake is that you have some distribution of people's feeling thermometer about gay marriage. And then you go and the study is that you go and you have them talk to a gay person for 20 minutes, and then a month later you ask them for their feeling thermometer again, and you see, do they feel more positive about gay marriage? Did the conversation help them feel good about gay marriage, or did their opinions not change? How does that change? And it was this huge study, because the outcome was that everything went way up. People suddenly, they were like, yeah, I support gay marriage. I had a conversation with a gay person.
They were normal, turns out. What? And so this was a big revolutionary study, and what it did is it actually informed how a lot of people went about sort of canvassing. So if you're trying to convince people to vote for something, this study, if you read this study, you were thinking, hey, we need a lot of people to go out and talk to people about this. This actually had a real life effects out there in the world.
So this was a big study. There was only one small problem with this study, which was that it was fake.
It didn't actually happen.
And the way that it got caught is kind of stupid. Because what these guys did is they took a real distribution of people's opinions based on a previous study, and they just modified it very slightly to try to make it look like they'd regathered the data.
So what that means basically is they did a feeling thermometer, much like this, how we said you like Frozen, and then let's say, well, we really want people to like Frozen. So what if we just kind of took all of these and just sort of, moved them a little bit? We can just take them and sort of move it, move some just a little bit. We'll take somebody over here.
And so,
Take somebody over here.
So that's literally what they did, is they took
move
their
them
original
over here.
feeling thermometer and they said, let's not actually conduct the study. We'll just sort of say what it should look like. We'll just move everyone forward a little, randomly. Kind of, a few people will go forward 1, a few people will go forward 2.
Maybe
a
one
few
person
people
goes
stay
back
where
a
they
little
are, right? But what they didn't realize is that what this does is it takes away the property that it takes away the human psychology of it, which is you have all these 50s turn into 51s and 52s and 49s and 53s.
If you look at this now, we don't really have all that clumping, that nice clumping that we saw before.
And that's not consistent with human psychology. And so, by forgetting what the feeling thermometer should actually look like, they got caught. Which kind of takes us to sort of what's the beginning of a theme, which is if you're going to fake a study, if you're going to fake something like, say you did your homework or something like that, you shouldn't just fake the outcome, you should fake the process. So for example, the process here is that you have real human psychology leading to the distribution of the numbers. So how do you fake that process? Well, you do the first feeling thermometer, and now you want to figure out how to turn that into a second feeling thermometer, which looks kind of like the first but slightly better. So how would you do that?
You move all of the clump forward or backward.
That's a great idea. The only thing about that is even though you would still have clumping, you would end up having clumping in some weird places. Like you might have clumping on the number 52 or something, which would then look bizarre, because why would people pick 52? That's sort of not, it turns out that in thermometer surveys, feeling thermometer surveys, that doesn't really happen. But that's a really great idea. Let's try to somehow use...
Well, you can move the clumping to another number
still.
divisible by 5.
That's a great idea.
That is a good way to do
That's
that.
also a great idea. So this is exactly the kind of thinking they should have been using. And so sort of one way you could do this is you could say, okay, well, we know what feeling thermometers should look like. So let's just say, okay, let's take our current feeling thermometer and take the clumps that already exist and make them larger, and take some clumps back here that already exist and make them smaller, but not changing where the clumps are or anything like that. And by doing that, you can sort of keep the process of this is how human psychology works, this is where the clumping is, and then maybe they wouldn't have gotten caught.
And a way that, if you really wanted to get hardcore about it, a way that you might be able to do this is actually just take another feeling thermometer, but about something that people feel less divided about. So instead of Frozen, you talk about, I don't know, the Avengers. So some kind of a movie, or, in this case, you give it a different feeling thermometer, and this way you have actually faked the process where you have actual humans making actual decisions, and that gives you that nice clumping, but in a more positive
And
space.
then all you have to lie about is the caption of the feeling thermometer. So you get a feeling thermometer on actual opinions of gay marriage, you get a feeling thermometer on the Avengers, and then you relabel this feeling thermometer opinions on gay marriage after discussions.
Yeah, and what that would do is that would be almost impossible to detect mathematically, because it's going to be generated by the same sort of random variable process that your first one is made from.
Awesome. So, are there any questions so far? We've got about 15 minutes left, and we've got one last exciting one. We've got, I guess, 2 more exciting things to show. We're just gonna quickly breeze over one other example
Of faking the process.
And this is actually a much larger scale example. So far we've been talking about, okay, if you're in academia, how do you fake a study? If you're a drug company, how do you sell your drug? But what if you don't want to just take over a drug or take over academia? What if you want to take over an entire country, right? And I know that's really why you came to the classes. Almost all of you want to take over a country, and so do we. So we decided to learn a little about how do people go about doing that. And one of the most interesting ways is through election fraud. You have an election, and then you just sort of fake how the results came out, and you say, aha, I've been elected president. Oh, awesome, right? Which is great, except for one small and not so small problem. It's called Bedford's Law.
And so what Bedford's Law is basic. Well, before we talk about Bedford's Law, let's talk a little bit about these sort of election frauds. And so typically, if you're thinking about an election, one way that you might decide to fake it is you take the ballots, and instead of you take a ballot that might have a whole bunch of votes for one person or another and another, and you replace that with a ballot that just has a whole bunch of this one candidate that you really want to win, right? Well, it turns out if you start to do this, you start to mess with sort of this thing that's like this normal distribution. You start to mess with math, and in particular, you run up to something called Bedford's Law, and And this is what Bill is writing here on the board. And what Benford's law states is basically if you have any natural process that spans many orders of magnitude, so basically we have 1, then 10, then 1,000, then 10,000 and stuff, that's an order of magnitude. If you have a natural process that scales across that, like an election, it turns out it follows something called Benford's law.
So what Benford's law says is, okay, suppose you have a whole bunch of numbers, and you have a whole long list of numbers, and you look at their leftmost digit, that is the leading, most significant digit. And you look at how often is that digit a 1? How often is that digit a 2? And so on. Then what you'll notice is that actually 1s are a lot more common than 2s, which are a lot more common than 3s, and so on. So why would that be the case? Well, sort of the simple analysis of that is that it turns out if things are uniformly distributed in terms of their orders of magnitudes, then that's the kind of thing that ends up happening. But now let's apply this to uncover an entire election fraud. So in 2009, the Iranian election came out with some pretty funky results. There were a lot of people saying, there's a lot of things strange about what just happened in the election. There were claims that more people voted in some districts than people lived in those districts. There were all sorts of funky things that were going on, so people decided to do an analysis of the votes using Benford's law. And in particular, in each town, there was a ballot box, and you could look at the tally for how many people voted for each candidate in these, ballot boxes. And what they found is that even though historically voting turnouts end up being well represented by Benford's law and the generalization of Benford's law, which is for 2 digits, in this election, for some reason, it wasn't represented by Benford's law at all. And the best explanation they could come up with for why that was the case is that someone decided to take the votes for one candidate, chop them off, and move them to another candidate, the winner.
And if you do this, you can see that this won't follow Benford's law, because you could be taking some of these chunks and end up moving them different places, and you end up with, when you do something like this, you end up with a Benford's law distribution. If you're looking at all of these numbers, 1, 2, 3, 4, 5, you end up with something that doesn't look like this. In fact, it ends up looking sort of wonky. You end up with lots of 2s.
The idea is, in nature, when you have actual humans voting, you get distributions of votes satisfying Benford's law. But then if you just decide to, without any real reason, just move some votes from one place to the other, chances are you'll figure out how to break Benford's law by accident. And then you'll be easily caught. Well, not easily caught. We know that they committed fraud, but they still won the election. So,
So even though we can be reasonably certain using this sort of mathematical analysis with Benford's law, we can be pretty sure that election fraud actually did happen in this case, based off of this research that some academics did. Even though that is the case, these people they're still in power. They still got to run the country.
So how would you fake the process instead of the outcome here? Well, faking the outcome is to say, okay, here's the end voters, let's just take some of them and move them over here. Faking the process would be saying, okay, let's add some imaginary voters with real voting preferences distributed through the districts, and then see how that affects our outcomes, and then that would have been able to emulate Benford's law. Okay, we want to conclude with one awesome story about how to make money in an ethical yet lying manner.
Before we talk about that, though, are there any questions about Benford's law or anything like that? Does that sort of make sense? This whole thing, is that interesting and stuff?
Okay, thanks, guys.
Okay, we were counting to 10 to make sure that anybody wanted to say something really could.
Okay, so the last story we're going to tell is this really cool story about these guys at MIT who went and decided to use math to lie in a way that cheated casinos out of their money.
And these people ended up making a lot of money from this. This is a great story. So why don't you erase the board here while I set the scene. So imagine you're a casino and you don't want people cheating on your games. Well, there's a way, if you look at blackjack specifically, which is 21, if you guys have heard of this game, if you count the cards, you can guess based off of probability distributions and what has already come up, what the next cards are going to come up. And this will give you an edge. This will actually, if you go and you count cards, you can actually win 21 more often than you lose. You can make an income this way. But casinos don't like this. They don't want you to do this. So what they do is they analyze and they watch people who are playing blackjack, and you can watch if somebody is betting really low and then suddenly bets high when the odds get good. When the odds get good, it seems pretty reasonable that this person therefore is counting cards, and you can get it.
Now,
Right.
the interesting thing about counting cards is that it's not illegal. Casinos can't send you to jail for counting cards. They can just kick you out of the casino. And so you're not actually breaking the law, which is why these MIT guys thought it would be a great idea to go and figure out how to count cards in a way that they wouldn't get caught. The problem was that casinos are really, really watching out for card counters. If someone is fluctuating their bets, and the way that they're fluctuating their bets corresponds with when luck happens to be in their favor, then they'll know that that person is counting cards and keeping track of what cards have already been played and what the odds are of the next cards being played. And that's a big problem.
Yeah. So you're gonna, if you do this, if you go to Vegas in 10 years from now, and you and you try to count cards, they're gonna be able to figure this out pretty much immediately. But what MIT did, what these students did, was a really clever way to evade this detection. And that was with using a group of people.
So, okay, if any one of us is fluctuating our bets wildly, then it'll be obvious that we're card counting. But suppose that this entire class goes to Las Vegas. And now, these four of us over here are going to be the high bettors. They go around to tables and they always bet a lot. And the rest of us are going to be the low bettors. No matter what, we always bet only a little. Now the low bettors go and they sit at their own tables. They go and sit at blackjack tables around the casino, and they count cards. But when the going gets good, when the cards are in their favor, they don't suddenly bet more so they can win money. Instead, they make some sort of sign. They cross their arms, or one person's sign was to say that I'd rather be bowling or something. And that's just true. I don't know why that was their sign. And you know, you have some sign, and then one of the high rollers, one of these four over here, comes over to your table having seen
They see the sign. They're like, oh wait, this table must have really good odds. And so they walk over there, and they aren't changing their betting patterns. They're always betting high. But when they bet high on this table, turns out their odds are in their favor, and they end up making a lot of money. And then, you know, they keep doing that until, you know, the odds run out here, and they see somebody over there makes a sign. They're like, oh wait, this table's really hot. I'm going to move my money over here
So
and continue to play over my cards over here, which basically means that I personally am not fluctuating my bets at all. We're still betting high. It just happens that when I bet high at whenever the odds are good. And
So
it just happens that
the clever
I
thing
move
that
it
the
around.
MIT students did is they said, let's understand mathematically how are the casinos analyzing cheaters, and let's cheat in a way that avoids that. So it's lying with math, kind of. And the way they did that is they had a bunch of people who always bet low and a bunch of people who always bet high, and just weirdly enough, the people who bet high are just incredibly lucky. And the casinos basically didn't catch on for a long time. And you know, they actually were so successful, they got, every year they would get 250% return on their money, which doesn't sound like a lot, except one year they had more than $1 million invested in them.
So they ended up making, for people that like invested in them, almost upwards of $5 million or something, for taking classes and then just on the weekends flying down to Las Vegas and counting cards and then flying back to take classes the next day, which is pretty incredible and kind of a cool thing that you can do with math.
Okay, so we're basically out of time. So if you guys have any questions or want to stick around and ask anything, that'd be great. If you have any advice for how to improve our presentation of this class, there's a Splash teacher review thing that you can fill out, and you can just write any advice or ideas you have. Or if you liked the class, you can write, you know, I liked the class, exclamation mark.
That sort of thing. We still have about 5 more minutes before this class technically gets out, but that's all we have to say. So you can go out and maybe just hang out for a little bit, whatever you want to do.
Or stick in here.
Yes. Thanks so much, everybody.